So now you know how to calculate matrix inverses. But in order to proceed with this chapter, we need to introduce a technique that is very useful for me to visualize things so that you can understand them much better. So let's go into it. This is how to use Venn diagrams to represent vector spaces. Okay, so let's do an example. Let's imagine I want to represent the vector space of the two-dimensional space, which we usually call the vector space R squared. Yeah. So this is a vector space in which an infinite amount of vectors are living. Yeah. Every possible vector you can draw in this vector space is living in this vector space. Yeah. So one way we can draw this using a Venn diagram is to say, okay, I'm drawing a circle here, and this is like my bag of vectors. Okay, so every single vector that I drew here on the left can be represented by a point on the right. Okay, and this will be R squared. Now, imagine that inside this vector space, I now draw a line. Remember from chapter 1, if this line crosses the origin, this line is in itself another vector space. It fulfills all the axioms of a vector space. So we could say that this is a vector space L for line. We give it this name, yeah? And this is clearly a subspace of R squared. Why? Because every vector inside this vector space L is also inside the vector space R squared. So in our Venn diagram that I'm doing here on the right, I know that every vector that is inside this bag called L is also inside R squared. So I can draw this circle, which is completely included inside the other circle. Yes? And also, for example, the vector v equals 0. This is in itself, it's also a subspace. Yeah, you remember the origin is a zero-dimensional subspace, which is inside the vector space L, which is inside R squared. So we could draw it here. This would be v equals 0. Yeah. But now, every possible vector is either, for example, this one here, A, is either inside the bag of the line, or, for example, this one here, B, this one is outside the bag. Yeah. And it doesn't matter where I draw it in the Venn diagram. What matters is if a point is inside a vector space or not. Yeah, that's what Venn diagrams are for. So this is how we can represent vector spaces using Venn diagrams. And now we can apply this to vector transformations. So for example, imagine a vector transformation which projects R squared into the x-axis. What does this mean? If we start with this vector v, we project it down to the x-axis and we end up with this vector a times v. If we started with this vector a, we project it down to the x-axis and we end up with this vector a times a. Yeah. In other words, no matter where we start, we always end up in the infinite line given by the x-axis. Yeah. So this we could call it a vector space, which we could call it x-axis. It is a vector space. Yeah. So we could draw a Venn diagram in which we have R squared, and inside of R squared we have our vector space, which is the x-axis. Yeah. Now think about what this transformation A is doing. This transformation A is getting every vector wherever it is, and it's pushing it inside of the x-axis. Yeah. Because every single vector is projected into the x-axis. You can also apply the transformation to a vector that starts within the x-axis. For example, you could get this vector here, vector c, and that would also be equal to vector a times c, because when you project it, it ends up on itself. So vector c would be some point inside the x-axis, which ends up on itself. Yeah, so we could draw an arrow, so this vector ends up on itself. An even better way of representing this, instead of drawing arrows, we can do this. We can say, okay, let's draw the input vectors on the left. So this will be the input space, and the output spaces on the right. So now what does the transformation do? The transformation gets points, such as point A, from the input. Let me use the same color, point A. And the transformation moves it to some point within the x-axis, which would be A times A. So this is applying transformation A. Yeah. Some other points, like C, they are inside the x-axis, and these points are mapped also inside the x-axis. They end up actually in themselves. Yeah, so we can draw it like this. And actually, a way we can show how this transformation is acting on all the vectors at the same time is we can draw the following. Let me remove this. So we could say that this transformation A is getting the entire R² vector space, and it is projecting it or changing it into the x-axis. So this will be the transformation A. And it makes perfect sense, right? So every single point inside this left circle ends up inside the smaller circle on the right, which is the x-axis. So we will use this very often in order to explain the concepts of the null space and the column space and so on. Thanks for watching.